trees. Okay, so now we're in a position to give a more general definition of trees than just the RBTs, the rooted binary trees that we discussed when we talked about recursion. So general trees. A tree is a connected graph with no cycles. That's an odd definition. Okay, so let's see. Let's play around with this. So, let's try to build a tree. Okay, so we start. Let's say we have 6 vertices. 3, 4, 5, 6. I don't know. Okay, so we're going to keep adding edges and see when we get a tree. Okay, so let's add an edge. So we add this edge. Okay, so let's add another edge. Let's add this edge. Okay, now let's add another edge. Well, maybe I can add this edge. So anyone see a reason why I cannot add that edge? Well, if you said, but that creates a cycle. Remember, we talked about a cycle. You start somewhere, you roam around on a path and come back, okay, and without repeating edges. And so this creates a cycle, so you cannot add that edge. Okay, so what edge can we add? Okay, maybe we can add this edge. Yes. Now, can we stop here? Are we done? No, because this graph is not connected. Okay, there are no cycles, but it's not connected because how does this guy get to that guy? So not connected. Okay, so we need to add more edges. Well, we could try to add another edge here. For example, this one, that would cause a cycle. So if I don't want a cycle, maybe I have to add an edge from in here to here. But I don't feel like doing that. Let me add this edge. Okay, good. Okay, I've not created any cycle, but can I stop here? No, it's not connected. So I have to add another edge. So let me add maybe this edge here. Okay, good. Can I stop here? Well, at least it's connected. So it's connected and it has no cycles. So I can stop here if I wanted to, but let's try to continue. So let's try to add any other edge. So let's try to add this edge, for example. There's a cycle. Let's try to add this edge. Oh, there's a cycle. So if we add this edge, we've got a big cycle. What about some other edge? What about this edge? From this guy to this guy. Oh, there'll be a cycle. Look, start here, go here, 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 here. Okay. So I cannot add any more edges. So not only can I stop here, I must stop here. Now, we sometimes typically draw this tree in a different way. So maybe this guy becomes the root. And so this guy has 3 children. So 1, 2, 3. So those are these 3 children. Okay. 1, 2, 3. This guy has no children. This guy this guy has a child, and this guy has a child. So this is another way to draw that tree that looks more like the rooted trees that we talked about. Okay. This is a perfectly well-defined tree according to that definition. And look, let's count the number of vertices. 1, 2, 3, 4, 5, 6. 6 vertices. And how many edges? 1, 2, 3, 4, 5. 5 edges. So number of vertices is equal to number of edges plus 1. Or the number of edges is the number of vertices minus 1. We proved this rigorously for rooted binary trees using the recursive definition. This is true for general trees. Okay. Now you can sit down and try to prove this by induction. And it's one of the exercises in the chapter if you're having trouble. Okay, let's move on. Okay. So move on. Planar graphs. Okay, planar graphs. Planar graphs. Okay, so let's take a situation where you have 4 friends. They're all friends with each other. So we say that's a clique. And since there are 4 of them, that's the clique of size 4. K4. So K4. And let's see how we could draw this arrangement of friends. Okay, so 1, 2, 3, 4 friends. And they're all friends with each other. So there. You see that there's an edge between every pair of vertices, and so that's the clique of size 4. And when you look at this, when you look at this, you say, "Oh man, this is ugly." And why is it ugly? It's not a clean drawing of K4. And why is it an ugly, non-clean drawing? Because look, the edges cross, so that leads to confusion. Okay, so it's bad. Edges cross in the drawing. Okay. I'll just mention where the word planar comes from. It's because the drawing is on a sheet of paper, in this case the blackboard, which is a plane. So I'm drawing on a plane. So planar graphs. Okay, so I'm drawing on a plane. And you might ask, well, isn't it possible to just change the way I draw the edges so that they don't cross? And indeed, that's the case. Okay, so here, my same graph with the same people and the same friends, but I'm just going to draw it differently. Oops. Okay, now everyone is friends with everyone else, and now when you look at this, oh, it's nice and clean. Okay, I used a curved edge, but that's not a big deal. It's nice and clean, no edges crossing. Okay, so this is good. None of the edges cross. Okay, and when the edges cross, we say this is a non-planar drawing. Non-planar drawing. And when the edges do not cross, we say this is a planar drawing. Okay. There are other ways to obtain a planar drawing. So for example, I can put one vertex here, here, and here. So now I connect this guy, and now look, there. That's another non-planar drawing. I'm sorry, that's another planar drawing. Okay, planar drawing. So there might be multiple ways to draw a planar a graph in the plane so that edges don't cross. And if the graph can be drawn in the plane so that edges don't cross, then we call this graph planar. And that raises the natural question, are there graphs for which there's no way to draw them on the plane without edges crossing? So is it always possible to get a planar drawing of a graph? Okay, so these are planar drawings of this graph. This is non-planar. So we say that K4 is planar. Okay, and the question is it always possible to get a planar drawing for any graph? And the answer is no. So some graphs have planar drawings and some graphs do not. The graphs that do have planar drawings we call planar graphs, and we love planar graphs. Okay? They're sort of simple in some sense. They're clean, simple. Okay? And why do we really care? Okay, as computer scientists, for example, is there any reason to really care? And so let's now bump it up a notch and consider, let's say, building a semiconductor chip. So it has processing units. And imagine that the semiconductor chip has, 5 processing units. And we want full connectivity. And so in semiconductor chips, you have your processing unit, and then you connect them with very fine gold wire. Why gold? Because it resists corrosion, it conducts very quickly, and so on and so forth. But okay, those are details. And in my case, gold is going to be red. Okay, so I want full connectivity between these processing units. Okay, so this guy must connect to all the other ones. Okay, this guy must connect to all the other ones. Okay, but now that I've connected here and here, I need to connect to these two. I cannot go through, so I must go round. So for example, I can go this way and I can go this way. Okay, so I've connected round. Okay, and now, this guy has connected to, this guy and that guy, and needs to connect to these two, but that's easy. Okay. And now let's look at this guy. He's connected to 3. He's connected to this, and this. He needs to connect to that guy. If he goes through, the edge, the wire is going to cross another wire. If he goes around, the wire is going to cross on that side. So this guy's got a dangling gold wire. This guy's got a dangling gold wire. And there's no way to connect them. Okay, are we sure there's no way? Yes. It turns out that we can prove there's no way. Okay, but for the moment, you can just try. Okay, because I'm just trying to show you why it's important. So we would like to connect with gold wire so that wires don't cross. So you might say, well, why do we care? Let's just cross the wire. Big deal. Okay. The problem is, now previously I said the non-planar drawing was bad because it looked bad, but now it's actually bad because when wires cross, okay, that leads to shorts or strange ways in which current will flow, because now if you're sending electrons down one part of the wire and you wanted it to go here, but they might go here. You can't control it. Electrons flow along the metal wires, along the gold wires. Okay, so this is actually bad. Leads to shorts in circuits and so on and so forth when wires cross. So you might say, well, why don't you just insulate them? We don't insulate the gold wire in semiconductor chips. It's just exposed wire. Okay, and we don't want crossing of wires. Okay, so in the early days of Apple, for example, Steve Wozniak was an ace at constructing planar drawings of chip layouts so that you could lay them out on a single layer of semiconductor. So what do you do in this situation where you need to have wires cross? Well, it's fundamental that wires cannot cross. Okay? So what you have to do is you have to escape from the plane, and so you have to add another layer. And so this wire will have to go into another layer, go across, and then come back down. Okay, but adding additional layers of semiconductors in the construction of a semiconductor chip just adds to the cost. Very expensive. So it's important to be able to lay out semiconductor chips as planarly as possible. Okay, so this is an example where you cannot do it. Are there other examples? Other simple examples? Yes. Let's consider 3 houses. So house 1, house 2, house 3. Okay, and you've got water, electricity, power, and sewer. Okay, and now you need to connect each house to each utility. Okay, so you've got to send the pipes or whatever it is. So you send the water, good. You send the power. Okay. Good. Okay. And you send the sewer. Well, you can send the sewer here and here. Okay, but how do you get the sewer to this house? You'll have to cross. In particular, maybe the sewer line, you send it this way, and the sewer line is crossing with the water line. Do you really want your sewer line to cross with the water line? This is sometimes called the utility graph. So if you're going to connect up all these houses with you, then you need to put these sewer and the water line at different levels in your graph. And then in the construction of houses, you have to have different levels for sewer and water and so on. It gets expensive. We would much prefer to be able to construct utility graphs as planarly as possible. Okay. Well, in practice, we just have a different layer for water and sewer and power perhaps. Okay. But you see, this is another simple graph that if you try hard, you won't be able to get a planar drawing. So this is non-planar. So K5, non-planar. K3, this is the 3 by 3 bipartite graph. Houses is type 1, utilities is type 2, and it's fully connected. So K3, okay, is not planar. Let me give you an example of a graph that is planar. So we're getting kind of depressed. Everything is non-planar. So let's consider a map with a bunch of countries. Okay, so I'll just show the countries as strange-looking polygonal shapes. So we have countries A, B, C, D, E, F. And you can imagine the countries are my objects. Okay. And 2 countries are related if they share a border like this. So if they're related, there's a border, so I can put the link between 2 countries that share a border, not just a point. Okay, they must share an actual border, not just a vertex, a point. Okay, so these 2 countries are related. There are 2 countries that are related. There are 2 countries that are related. Look, these guys are related. Okay, these guys are related. These guys are related. Okay, these guys are related, and these guys are related, and these guys are related. There. Okay, I've drawn a graph that represents the border relationship between countries, and look, almost by construction, it's planar. Okay, now. We like to color countries so that, you can easily make out what are countries. So here, I can color this guy, let's say blue. Okay. And now I can color this guy. So any neighboring country must be a different color. So I can color this guy green. Okay. Now this guy is neighboring both of those. So maybe I'll color this guy red. Okay. Now I have to color this guy something. So let me color this guy green. Which is okay because this guy doesn't border with A, and I have to color this guy. I can color blue because he doesn't border with B, so I can color blue. Okay, and now this guy doesn't border with F, so I can actually color green. In this particular case, I have a set of countries, and I can make it very clear what are the countries with different colors, and I only needed to use 3 colors. Okay. What's the maximum number of colors I need? It turns out the maximum number of colors you need is 4. Okay, and that's related to the fact that every planar graph, so this is an example of a planar graph that came from a map, but every planar graph can be colored with at most 4 colors. Where coloring a planar graph means color the vertices so that if 2 vertices share and are connected by an edge, they must get different colors. Okay, so application of planarity to maps. Okay, now. So let's take an example. Let's look at an example of a planar graph again. So let's take our K4. Okay, and you will see that the number of vertices V is equal to 4. Okay, the number of edges 1, 2, 3, 4, 5. So 1, 2, 4, 5, 6. So the number of edges is 6. Okay, I'm going to count the number of regions. These are called faces. So let me show you what the regions are. There's a region here. So this is a region. This is a region. This is a region. So we have 1, 2, 3 regions. Actually, there are 4 regions. There's this big, huge outside region, this unbounded region. So the number of regions, and we typically use the letter F. Actually, F stands for faces. The number of faces, 1, 2, 3, 4, is 4. Okay? And you will observe that if I add up the number of if I add up, so consider the number of faces, okay, plus the number of vertices, okay, minus the number of edges. So F, faces plus vertices minus edges. So faces plus vertices minus edges. So 4 plus 4 minus edges minus 6. This is equal to 2. Okay. Let's do it in this planar graph. Okay. So you will see that the number of faces is so the number of vertices V 1, 2, 3, 4, 5, 6. So V equals 6. The number of edges is 1, 2, 3, 4, 5, 6, 7, 8, 9. The number of edges is 9. And now let's count the number of faces. So the number of faces is interesting. Number of faces is here's a face, here's a face, here's a face, here's a face, okay, and here's a face. 1, 2, 3, 4, 5. Okay, so here's a face. Well, 1, 2, 3, 4, 5. So the number of faces is equal to 5. Okay, this is the outside face, and then there are the 4 inside faces. So faces plus vertices minus edges is equal to 11 minus 9, which is 2. Euler proved this general result, that if you have any planar graph, okay, then the number of faces plus the number of vertices minus the number of edges is always 2. Fascinating. Okay. It turns out that this what's called the Euler invariant of a planar graph, this plus this minus that. This Euler invariant is instrumental in showing that these two graphs cannot be planar, because you can think about what that must entail. You must show that there's no way to draw these graphs on the plane, on a sheet of paper, so that there are no edge crossings. Try and do it. Try and get a planar drawing. You won't get one. Okay, but how to prove that there's no way to do it? You don't have to consider all planar drawings. You have to use much more sophisticated arguments and that are related to Euler's invariant. And you can see an exercise in the book that actually does that, okay, if you are interested. Meanwhile, let's move on. Different kinds of graphs.